So this week we continue our discussion of spinors. This is all part of the workup to being able to discuss supersymmetry and the supersymmetry algebra in a nice way. Today I'd like to discuss the notion of a spinor inner product. This is a way of taking two spinors, putting them together, and getting out a number. So let's get started. The spinor inner product. We already saw last week a rather irritating feature of spinors. We saw that if we want to take a complex conjugate of a spinor and impose some reality condition, then the natural thing to do is actually not to set the complex conjugate of the spinor equal to itself, it's to set it equal to some matrix acting on that spinor. This was this way of imposing a Majorana condition, and at least personally I feel it a little bit distasteful. I spent all of this time in elementary school and beyond learning about complex numbers and what a reality condition should be. And now finally I get to this stage and someone tells me, aha, but for spinors, the way you impose a reality condition is different, which makes me think, well, maybe you didn't set things up right to begin with. But there it is, that's how it works. Another annoying feature about spinors is that if you were to do the obvious thing, which would be to say, take the Hermitian conjugate of your vector, your four vectors, say for the case of Dirac fermions in 4 dimensions, and just sandwich that with the original spinor, that's not a Lorentz invariant scalar. That if you want to define a Lorentz invariant scalar, you're going to have to work harder. And I also find this a rather distasteful aspect about spinors. I don't know, maybe for some people they like these extra complications, but it would be so much simpler if we didn't have to worry about it. Well, let's see what the issue is. Let's see what the issue is in more detail. So let's recall how to perform a Lorentz boost or an infinitesimal Lorentz boost on a spinor. So recall we did this way back when, I think in the second week. If we have a spinor, and let's put back the spinor index, although we'll typically suppress it, the infinitesimal boost or rotation under the Lorentz group, we can describe it with some antisymmetric matrix omega contracted with these gamma matrices, gamma mu nu, and here are my spinor indices again, alpha and beta, psi beta. And let's just recall that what I mean by this gamma mu nu, I mean the antisymmetric combination, gamma mu, gamma nu, minus gamma nu, gamma mu. And this will in fact equal gamma mu, gamma nu, if mu is not equal to nu, and will just vanish otherwise. All right, so that's how we did a boost, and now this will imply that if we look at the Hermitian conjugate, a delta psi dagger, we can write this as 1/4. Now we have to reverse the order, as we do when we take the Hermitian conjugate of psi dagger, omega mu nu, gamma nu dagger, gamma mu dagger. In fact, it doesn't matter too much where we put this omega mu nu parameter. This is just a number compared to the other quantities here, these spinorial quantities, the gamma matrices and the psi. So we could actually put the omega mu nu wherever we want. But the other things, those are matrices and vectors. We have to pay attention to their ordering. Okay, so that's where we are. And now I want to show you why when I sandwich psi dagger with psi, I don't get a Lorentz scalar. So we have to analyze this boost a little bit more carefully. I have to understand how to take the Hermitian conjugate of the gamma matrices themselves. So I have a little claim here I'd like to prove. The claim is that if I take the Hermitian conjugate of gamma 0, I get minus gamma 0. Whereas if I take the Hermitian conjugate of any of the other spatial ones, I'm going to get the gamma i's back. So the gamma i's, the spatial gamma i's are all Hermitian, but the time-like one is anti-Hermitian. So let's see why this is true. Let's just analyze it for a particular example. Let's look at the 4D case where we had this basis of gamma matrices, this Weyl basis so-called. So we have a sigma mu in the upper right, this sigma bar mu in the lower left, a 0 and a 0 on the diagonals. And sigma mu is some 4-dimensional generalization of the Pauli matrices. So I've got the identity, and then sigma I, and then the barred guy. For the barred guy, I'll flip the temporal component and keep all the others the same. So I claim this is a good basis for the gamma matrices in 4 dimensions, which has the right anti-commutation relations. And now if we stare at this a little while, and we recall that sigma I dagger is equal to sigma I, we can see that this claim up here is going to be true. Because if we look at the temporal component, where we have the identity and minus the identity, in this gamma matrix. So when we take the Hermitian conjugate, we'll indeed get that extra sign. Whereas for all the spatial guys, since the Pauli matrices, the spatial Pauli matrices, the sigma I are all Hermitian on their own, we won't get a sign. So that's in one basis, and now I claim if it's true in one basis, it's going to be true in every basis. So why is that? Well, how do we change the basis? We take some unitary matrix and we conjugate it with a gamma matrix. So we send gamma mu to U, gamma mu U inverse. So that implies that if I look at the Hermitian conjugate, that will send the Hermitian conjugate to U inverse Hermitian conjugate, gamma mu Hermitian conjugate, U Hermitian conjugate. But for unitary matrices, the Hermitian conjugate is the inverse, and so I can write this as U gamma mu Hermitian conjugate U inverse. And from that, it's clear, right? Because the sign, I can just move that through the unitary matrices. And I'll let you, as an exercise, if you will, I'll let you check the case for general D, for general dimension. All right, so that's how we do this Hermitian conjugation. There's one more thing I want to show before I move on and consider this Lorentz boost. We have this claim up here. We have this claim about what happens under Hermitian conjugation. And there's a further claim. I can write this a little bit more covariantly or compactly. There's a further claim that I'll add here that I can write this gamma mu Hermitian conjugation as conjugation with the gamma zero matrix. And you can see sort of directly why that's true, because if that mu is equal to 0, well then gamma 0 is minus 1, and that gives me the minus 1 here for the Hermitian conjugation of gamma 0. But if mu is a spatial index, then I have to anti-commute the gamma 0 through the gamma mu. So then I get a minus from that anti-commutation and a further minus from squaring gamma 0. And so at the end of the day, I'll get the plus sign here for the gamma I Hermitian conjugate. All right, so with that under our belt, we'll take this further claim to the next page, along with our result for how the Hermitian conjugate of the spinor transforms under Lorentz boosts, and we'll keep moving. So there are the two results that I need to move forward. So I'm going to replace the Hermitian conjugate of the gamma matrices with this formula, this gamma 0, gamma mu, gamma 0, and see what happens. So I get a 1/4 psi dagger omega mu nu, gamma 0, gamma nu, gamma 0, gamma 0, gamma mu, gamma 0. Great. Okay, and now I recognize the gamma 0, I can simplify that to be minus 1. And then further, what I'm going to do is I'm going to swap gamma mu with gamma nu. That's going to give me another minus 1. And so the sign is not going to change here on the next line. I'm going to write this now as 1/4. Remember, that mu and nu has to be different, or they would contract to 0 with the antisymmetric omega tensor. And then I can further write this in our compact notation as gamma mu nu, gamma 0, in the final line there. All right, and now we kind of see there's a problem. There's no way for this term to cancel against the Lorentz boost of psi itself. If you remember, we can flip back a few slides and compare this guy with what we had before. So there I've copied and circled in blue this formula we had before for the Lorentz boost of the unconjugated spinor. And for psi dagger psi to be a Lorentz scalar, the idea is that these two terms, the one we calculated and the one we started with, they have to cancel somehow. And there's no way for that to happen. We don't have the right sign, and we have all these extra gamma 0 matrices floating around. So something's wrong with this notion of an inner product. It's not a Lorentz invariant scalar. But in the sickness lies the cure. The sickness seems to be this proliferation of these gamma 0 matrices. And maybe if we add just one more to the mix, we can get everything to get fixed up. And so the idea here is that we're going to try using, instead of a Hermitian conjugate, we'll introduce a new notion of conjugation, this barred notion. And psi bar is going to be psi Hermitian conjugate with this extra gamma 0 matrix. And now things are going to work out. So if I just look at what we had up here, I think, sort of directly read off what the boost is for psi bar. I just add an extra gamma 0 at the end. So I'm going to find this as 1/4 psi dagger omega mu nu, gamma 0, gamma mu, nu, gamma 0, gamma 0, right? And, well, this gamma 0 at the end, I can replace that with -1, and this gamma 0 psi dagger combination, I can replace that with psi bar. And so what do I find? I find that the infinitesimal Lorentz boost I can write a little bit more compactly as -1/4 psi bar omega mu nu gamma mu nu. And now this will work. This will work. While this won't cancel, this pairing, because I have the wrong notion of the complex conjugate, or the Hermitian conjugate rather, these two will cancel, and I will see that this combination psi bar psi is a Lorentz scalar. So let's see how that works. All right, so I've copied out the relevant transformation rules for psi and psi bar, and now let's see what happens to the proposed scalar quantity. So suppose we have a spinor zeta bar and a spinor psi, and I want to compute the Lorentz boost of this. So I'm going to have delta zeta bar psi plus zeta bar delta psi, and now I plug in the rules. So I'm going to find -1/4 zeta bar omega mu nu gamma mu nu psi plus 1/4 zeta bar omega mu nu gamma mu nu psi. And now I have the right minus sign, plus sign. I've got the same things in both terms. Finally, I find that that boost is 0, and so I can conclude that zeta bar psi is a Lorentz scalar. Great. So I've identified how to appropriately take an inner product for spinors. So let's keep moving along and think a little bit more about what this inner product allows us to do, and how other things that we've developed, like the Majorana property, interact with this inner product. So a claim, the inner product allows us to construct other Lorentz covariant quantities. Well, we saw the scalar already, but there are other ones. One is what you get when you sandwich a gamma mu matrix between two of these spinors. This turns out to transform just like a vector under Lorentz, and I've assigned an exercise to show this. And you can keep going, as you might imagine. You could, for example, use this antisymmetric quantity gamma mu nu sandwiched between the two spinors, and this will give you an antisymmetric tensor under Lorentz. And the fun continues. Put what you like between the two spinors, appropriately symmetrized, and you'll get a nice Lorentz covariant quantity. So the next thing I want to ask is, how does this new notion of conjugation, this new notion of dagger, which we're calling bar, how does it interact with the Majorana property? So we just follow our noses here. So by definition, we have that psi bar is equal to psi dagger gamma 0. And psi dagger, well, that's the same as psi transpose complex conjugate times gamma 0. And by the Majorana property, this is the same as psi without the complex conjugation, B transpose gamma 0. And so because of this, it's nice to define a new matrix, we'll call it C, which is B transpose gamma 0. And it's sometimes called charge conjugation. And so the inner product for Majorana fermions, I can equally well write not in terms of gamma 0, but in terms of this transpose and action with this new matrix C. And then given that there's, in fact, more Lorentz covariant objects you can construct that use the C matrix. So there's a scalar quantity I can construct, and there's a vector quantity. In strict analogy to what we did before with the Bard conjugation, there's a antisymmetric tensor. And again, you can have fun and insert as many of these gamma matrices as you want and construct more and more of these objects. Although eventually the process will terminate. Okay. There's one more remark I'd like to make here. So we had before that gamma mu Hermitian conjugate, I could write that as gamma 0, gamma mu, gamma 0. There's an analog here for transposition. Here gamma mu transpose is the same as C gamma mu C inverse, where C is this charge conjugation matrix. And I'll let you show that as an exercise. You can use the same kind of techniques that we were looking at when we showed the property for Hermitian conjugation. I should maybe say a little bit about why I'm developing all of this technology. So when I introduce the supersymmetry algebra, one important thing is that we're gonna use Majorana spinors to write down the supercharges. So we're going to need a notion of Majorana spinor to talk about the supersymmetry algebra. And another thing that's in the back of my mind here when I'm introducing all of this is that we want to write down actions and Lagrangians that have nice properties under Lorentz transformation. And actions in Lagrangians are scalar quantities, and so I definitely need to know how to write a Lorentz invariant scalar to write down a supersymmetric action that involves fermions. So those are some reasons for why we're going through all of this. I know this is the second week of developing all this spinor technology, and you may be losing patience, but hang in there a little bit longer. We'll get through it, and next week we'll do some very interesting things with the supersymmetry algebra. So before we close this lecture, I want to talk a little bit about how to work with this technology. So let's talk about how to manipulate these spinors. So spinors for me, they're going to be Grassmann valued fields, and that means they anti-commute. They're not valued over the usual number fields, they're valued under some anti-commuting number field. And so that means that if I take two spinor components, psi alpha and zeta beta, for example, and I flip their order, then when I flip their order, I have to introduce a minus sign. This is not a universally accepted convention, so whenever you're reading supersymmetry papers, you have to take some time to figure out what their conventions are and see if they're the same as yours. They almost surely won't be, and if they're not, how to get from your conventions to theirs. And another thing I need to do, which is unfortunately not a universal choice, but it's what we'll use in this class. We need to choose a definition for complex conjugation, given that these quantities are now anti-commuting. And so I'm going to use the following definition. If I take, again, two of these spinor components, and I take a complex conjugate, I'm going to flip their order without changing the sign. So I'm going to write this as zeta beta star psi alpha star. And again, you have to watch it because sometimes people, they don't always use these conventions. So I'm defining this to be like the dagger or the Hermitian conjugation on matrices. And the other really important point I want to make here is that this is for components. And a lot of the pain is coming because we have this extra structure, the gamma matrices and the fact that we have a vector's worth of these spinor components, and those also have their own anti-commutation relations. And so we have to kind of put all of this together to figure out how to manipulate these larger objects, these larger scalar or Lorentz covariant objects. I'd like to do an example to give you kind of a flavor for how these arguments go. So let's take two spinors and let's say that they're Majorana. So they're going to satisfy this Majorana condition under complex conjugation. And I want to analyze the reality properties of this scalar, zeta bar psi. So let's take a complex conjugate and see what happens. Now because they're Lorentz, because they're Majorana, I can replace the bar, as we discussed just a few slides ago, with this C matrix and the transpose. And okay, so now let's keep going. And I want to use a trick. I want to use a trick here. So I've been yammering on and on about how usually this B matrix, or equivalently the C matrix, it's not just the identity. However, if you're clever about your basis, it can be. So we're going to work here in a really real representation where the gamma mu are all purely real, which means we are able to choose B to be the identity matrix. If we change our basis, that will no longer be true. But if we choose all our gamma matrices cleverly to be purely real, then we can just consistently choose B to be the identity, and then psi star will be psi. This will in turn imply that C, which is essentially just gamma 0, which is a gamma matrix, which is purely real, that C is also a real matrix. So given that, let's see what happens. So we can maybe restore indices to make it a little clearer what's going on. So we have zeta alpha, C alpha beta, psi beta star. Now by definition of complex conjugation, we can flip the order and write this as psi star beta, C alpha beta, zeta alpha star. And because C is real, the complex conjugate gives C back. Now we'll use the Majorana property. We know that B is the identity for this really real representation, so we can just replace psi star beta with psi. We have C alpha beta zeta alpha. This was by the definition of star. This is the fact that it's Majorana. And now finally, I'm going to flip. I'm going to use the fact that these are Grassmann numbers to flip psi and zeta, and that will give me a minus sign. So I'm going to get zeta alpha, C alpha beta, psi beta. So again, this is because they're Grassmann. And now finally at the end I can write this as minus zeta bar psi. Now there's something rather curious about this, that this scalar quantity we've written down, if I take the complex conjugate, I get minus itself. So this implies, right, that zeta bar psi is pure imaginary, which is maybe not what you were expecting. I mean, usually when we define these things in linear algebra, we define these inner products to give you positive quantities. So here we're defining it to give you a pure imaginary quantity. That's a little bit of a fault of the way I've set up the formalism in this class, but it's the way it is and we'll live with it. It's the fault of our conventions. I'd like to make a remark about what happens if you choose slightly different conventions. I'll just point out, like, in many places you'll see that psi bar is not just psi dagger gamma 0. There's an extra I in the definition, an extra square root of -1. And so if you'd done that, then you would have found that this inner product is a real quantity. Another thing you could have done is change the signature of the Minkowski tensor to start out with, which changes how you set up the anti-commutation relations for the gamma matrices. And this also can wreak havoc in signs later on. And I believe you can use our definition for psi bar without the I and flip the signature for the Minkowski tensor. And in that case as well, you'll get real quantities for this zeta bar psi quantity. So you would change the signature to mostly minus. So in either of these two cases, I believe zeta bar psi becomes real. Of course, if you did both, you'd be back in the pure imaginary case. So there's all these little conventions that you have to pay attention to if you're reading other textbooks or reading papers in the literature, that people often have their own conventions. There are all these little places to choose different signs. You just have to stay alert. Okay, so before I leave you, I'd like to assign an important exercise that will be very important in checking supersymmetry in the later lectures, checking that certain actions, certain quantum field theories are supersymmetric. And it will give you some practice in using this inner product. So the exercise is the following. It's to show that if I take the following sandwich of spinors, so I'm using this Majorana inner product, lambda transpose C, a bunch of these gamma matrices, another spinor chi, this is the same as -1 to the p chi transpose C, gamma mu p, gamma mu 1 lambda. So again, we will have reason to use this heavily in a couple of weeks when we start looking at supersymmetric field theories. Okay, so I'm going to leave you there. We have a couple more things to do this week before we put spinors to rest. So the next time I want to talk about Fierz identities, which are also going to be important for thinking about closure of the supersymmetry algebra. And in the final lecture, which is going to be optional, I want to talk about a slightly different formalism people often use in the supersymmetry context. It's called the two-component or the Weil formalism. And that will be it for this week. All right, see you next time.